we like introduced logic and talked about propositions, predicates. So that is like kind of the base layer of like math. And may I remind you, the goal of this is to like develop the mathematical language to discuss theoretical physics, right? And so the logic was the base layer. Then on top of that layered set theory, which is like it's formulated in logic as like the foundation of other math, right?
Like an axiomatic system or something.
Yeah, an axiomatic system. And so using that axiomatic system, so introducing another layer, we introduced topology, which is like a way to give structure to sets, right?
Okay.
And so that
how does the classification of sets fit into this story?
Classification of sets. Well, I think that like that lecture 3 or the classification of sets, like classification of sets was only like one thing there. Like there was actually a lot of other topics we covered. Let me just take a look at the notes and see how I can fit this in. Yeah, so I believe that it was like a lot of it was like a lot of terminology and like concepts that we could use to like deal with sets, right? And because topological spaces, which I was going to get to next, and like all the other structures or concepts we introduced later are either sets or they're based on sets, like having the ability to like deal with sets, like for example, even just like a simple as like classifying a set as finite or countably infinite versus uncountably infinite, like maps, pre-image, like all the like equivalence classes, this type of stuff, it is useful as like a way to deal with sets generally. Like it kind of gives us the toolkit to work with sets without like topology included yet. So that's kind of like what the lecture 3 was. Then lecture 4 was, and then after that, after we introduced sets, and then we introduced some tools to deal with them. Then the next thing we did was we introduced topology as a way to give another, like, because I think like if you look at like countably infinite versus uncountably infinite, that's a classification of a set, right? And so topology, I think, is like, it is a fundamentally new thing, but it's the same way of like kind of us adding like an understanding or like equipping a set with some other structure, right? And so we kind of like added a new way to think about things in terms of neighborhoods, maps between things, like continuity and stuff like that, when we introduced topology. And then topological manifolds are a subset of a topology, which is like what is being introduced now. It's a type of topological space. So you could think of it like a topological space with tighter restrictions that have nice properties for us in terms of representing. I think it's a way, like they're useful in representing objects. Like I think the use of them is that they're I don't know. I'm kind of conjecturing here in some sense because I'm not like familiar with the physics, but it seems to me like mapping an object's movement in like in the real world to a topological manifold could be very valuable, as he kind of like introduces that concept in the gravity and light lectures. It's just like another way of, I think the way I see it is it's kind of there are like some properties on in topological manifolds that that are useful when describing our physical world. I believe that's like the way to say it. And so that's why we're studying them, and then we're gonna like build on top of them as well. So it's not like the fundamental thing. Does that make sense?
Yes, 2 questions. Number 1, if lecture 3 was the classification of sets, and we talked about, or you mentioned that happens in terms of cardinality, what is the classification of topological spaces?
What is the classification, like, so the way that it was formulated in that cardinality, when cardinality was introduced, it was to say that within these cardinality classes, sets are homeomorphic between all the sets in one class are homeomorphic. Basically, there are structure preserving maps that exist
Oh,
between
are you,
classes.
are you sure homeomorphic would be the right word? I think isomorphic would be more accurate,
Isomorphic. Yeah, that's
or
the
even bijection.
distinction. Yeah, there's a bijection, but it's not necessarily it's the difference between homeomorphic is it's also invertible. Um,
No, I think homeomorphic is specifically for topologies. Like
fascinating.
if bijection is the word for sets, then homeomorphism is the word for
Right. Yeah,
topologies.
so they're isomorphic, and that means that there exists a bijection between them, and that is a way of preserving structure between the transformation between these two sets. And so in topology, so this is interesting. I watched some of lecture 5, and what I see it as is that there are some characteristics of topological spaces that are that maintain that are like maintained after you do like after like a homeomorphism is applied, right? And so like some of them might be like T1, T2, like compactness, right? Um, but I don't know if there is a fundamental like classification of topologies. And the reason why I say, he also says this in the 5th lecture. He says there is no list of attributes of a topology where I could give you like all of them, and you could use that list to like determine whether two topological spaces are equivalent. Like that list is like not of a finite size. And that leads me to believe that there are some classifications we can use to like, you know, group topological spaces together. For example, one of them is that we can group all the topological manifolds into one group and then all the non-manifolds into another. But there is no like, I mean, obviously the other thing I told you about cardinality isn't like fundamental or anything, right? Like we could choose any other grouping, but I don't know what the grouping that is like most commonly used in topology is. Does that make sense to you? Like, I don't know if there is one and I'm just forgetting it or it's slipping my mind or something.
Well, I remember exactly that pretty famously topology cannot be classified fully. But
Yeah.
if you can actually help me here, when you say the characteristics for topology, like T1, T2, Hausdorff, compactness, what would be the equivalent characteristics for sets, which can be fully classified?
So these
Or I
are
think they're
really
also called invariants. So there's invariant
invariants.
topological
Yeah.
spaces. What are the invariants for sets, for classifying sets?
Interesting question. By the way, like I've only poked my head into that because I was just curious what was up in that lecture. Like I only watched like half an hour, so I didn't finish it. Um, that's an interesting question. What are the invariants for sets? Well, like the idea is just this is me conjecturing, right? Like if you apply a homeomorphism to a topological space that is T1, then you're going to get another space that's T1, right? That's why it's an invariant. And so in the set land, if you apply a bijection to a countably infinite space, you're going to get a set. You're going to get another countably infinite set. And so in that way, I think cardinality is one thing you can think of as an invariant. I don't know if there are more. I don't know if there are more because the idea behind a topological space is that the grouping of the elements, like the topology, gives a certain structure to it, right? Like he mentioned this in the second gravity and light lecture, right? Like if you have a set, right, you can kind of grind up the elements into a powder, like pour the powder on a table, and that's still the same set, right? Whereas like if you had a set equipped with a topology, you can only like stretch it, you can't like cut it because there can't be discontinuity. And like, by the way, that analogy is still kind of melting my mind. I kind of don't get it yet, but for me, that just like the implication of that is that like there are many more things that are invariant with a topology because it's like a stricter like set of constraints being set on like an object, mathematical object. So like in basically like if you think about like a isomorphism or a homeomorphism, changing the contents of the set, right? Like changing the elements. Like you can map 1 to 2, right? Or whatever, right? In your map, you can like add 1 to every element. Then like that's kind of like changing the color of a powder, right? But like you can't, there's no more structure there. And
Uh-huh.
so like the idea of like compactness doesn't even really make sense, right? Um
Well,
and
hang on.
so
Like with your example, like let's say you have, yeah, the set 1, 2, 3, then you
yeah,
have the set triangle, square, circle.
yeah,
From a set point of view, if this is nautical with a topology, if these are both powders, they're both identical powders. They have the same behavior, cardinality wise.
that's right. Yeah, that's kind of what I was saying. But
Okay.
like and when you say it like that, I mean that was a more accurate way of saying what I was trying to say, which is that I believe cardinality is like the only invariant in set land because there isn't more structure than just the elements of the set. And if all the elements are the same, like from a behavior POV, right, then cardinality is really like the only thing that matters, like in terms of like the behavior of the set. Whereas like in topology land, it's just like much stronger what you can say about the set because there's more structure. And so we can say all these things like T1, T2, compactness, all this stuff, right? And where like those concepts just don't exist in terms of like a set. So
Yeah.
I would say the invariants are just entirely cardinality, and that's it.
Cool. Okay. So yeah, the only invariant for sets are cardinality.
Yeah.
By the way, if that was conjecture, I can give a stamp of approval and say correct. Conjecturing.
Okay, cool. Conjecture approved. All
Yes.
right. Okay, cool. And so topological manifolds are like a level on top of topology, like topological spaces. Um, and you know what's really interesting about this lecture I just watched, this lecture 2 in the gravity and light lecture, that he didn't really tell us that much about how they're used or why they're important yet. And that's not anything like I mean, that happens in math all the time. So I can tell you about them, we can talk about them, but it's similar to like topology last lecture where it's like, well, like as I was learning the topological manifolds lecture, I kind of like got more familiar with like, oh yeah, the topology does like set certain constraints around how you can manipulate the set, right? And so that now it kind of makes sense why we even use that abstraction. But like for topological manifolds, it's not clear to me yet, right? And so
Maybe one question is, I believe at the first lecture in the gravity and light, he says space-time is a 4-dimensional topological manifold.
that's one, yeah.
Do you have like an analogy for why that's true? Like if a manifold has like charts and whatever, like what is the chart of space-time?
What is the chart of space-time? Oh, that is so this is like one thing I was always trying to wrap my head around when he was like saying this in his lectures. He was saying like or the second, like in the topological manifold lecture, right? I'm just gonna abbreviate topological manifold as manifold because it's like
Yeah.
long.
That's cool.
For the manifold lecture, he was saying that if we have some object in the real world in RD, right, and we're mapping it using a topology to like another, we mapping it to a manifold using a chart map, right? And then like he made some statements about that, like, are we allowed to, say something about the real world object using our mapped object and stuff like that. And I was like thinking to myself, like, so like what do physicists think of the real world as? Is it really like RD, right? And like that sentence he mentioned in the first lecture was something that was like popping into my mind because like this is just like my intuition as like someone who is like knows something about physics, right? Is that it's we live in 3-dimensional space, right? So why is it a 4-dimensional manifold? It's because there's like a time dimension, right? And so that's like the 4th dimension, as in like things are changing as time goes on. So you can think about, you group time and space together, it's a 4-dimensional, like we're navigating through four dimensions, and obviously we can't back and forth in time, we can only move forward, and so we only think of things as 3-dimensional, and time is just like progressing, although in some situations time doesn't necessarily have to progress in the way that it does right now. But and that's like why it's four dimensional. But how does that kind of go back to chart maps and stuff like that? I'm not really sure, because like, he was always saying that like it's now and then like I was also trying to wrap my head around like, oh, you know it's local, like the definition was like, a topological space is a n-dimensional manifold if for each, it's locally homeomorphic to an n-dimensional, or you can map it to Rn, right? Like locally, right? So what does mapping something locally to R4 look like? I was just trying to, like, obviously it's like pretty hard for us to visualize that, but I
Well,
wasn't sure.
what about right now? What I see with my eyes is a local representation of space-time, where I'm the center of the universe, and there's 3 dimensions plus time. So in a sense, wouldn't it be accurate to say that I am looking at a chart of the universe right now?
But like I don't know if that I kind of jive with that, because I think like the way that I'm perceiving the world right now is it's a 3-dimensional space, and I'm just and it's just progressing, right? So I don't really like feel the 4th dimension like as time goes on. Like I'm like, you can imagine like snapshots of a 3-dimensional space, and each of them are just 3 dimensions, right? And so like I don't know what moving backwards in the 4th dimension looks like or feels like or anything, right? And so I would say that we perceive, from my POV, we perceive things in 3 dimensions, and then the 3 dimensions are changing over time, right? Like just like how you can have a 2-dimensional space with like a function that like over time with there's like you can have like a time dimension, like a differential equation or something, right? And I believe you can map that in 3 dimensions, right? But like looking at it in 2 dimensions is a very different experience than looking at it in 3 dimensions, right?
Yeah.
Make sense?
Yeah. I mean, that feels like a similar statement, like if you were living on the surface of the earth and you said, oh, the earth is flat because everything around me is flat. Like,
but I'm not saying it's necessarily true that there isn't a
oh,
4th dimension. I'm
okay.
saying that the idea of like what does an isomorphism to a what does a map to a 4th dimensional space look like? Like that was kind of weird to me. And all of this to say, going back to the thing, going back to your space-time is a 4-dimensional manifold. I didn't really get it yet because I couldn't like figure out how the world I'm living in right now, how I could create a map to a 4-dimensional like R4. Like I didn't get that yet. But maybe it actually is like, I could get there if we just like follow some reasoning line of questioning or something. You know what I mean?
Well,
But,
let's say that you're doing a physics problem on paper.
yeah.
And you have a building in front of you, but you write it down on paper. And you want to predict what will happen if you drop an object from the 4th floor. Wouldn't the representation that is on your paper, wouldn't that be a chart of the universe, because you can go forward and backward in time and see what happens when you drop a pencil, but it is just a local representative of the entire, whatever universe, space-time.
What is the chart? Wait, can you tell me one more time, like, what's the setup? Like, what are we considering here?
Like, let's say that you have a building in front of you.
Yeah.
And you want to, you're just doing physics, like you're solving a physics problem on an exam or something.
Yeah.
And that the problem is asking you what happens if you drop a metal ball from the 4th floor.
Yeah.
Wouldn't the picture of that on the paper be a chart? Because you've established local coordinates, right? You'll be like, okay, this is the 0, 0 coordinate, and then
sure, but like usually they like ignore a dimension in that picture, right? But that would be like a chart in some sense, right? Like usually ignore 2 dimensions. If there's a time dimension, right? Like on a like a physics exam, they just throw out the two dimensions and then they look at like distance and time, right? You know what I mean?
yes.
And then to visualize 3 dimensions, we have like an X and Y plane, and then there's like a Z plane for time, right? And so I suppose that if we're specifying that there are the coordinates of of something in 3 dimensions, right? And we were somehow able to like have that, right? And then we had a fourth dimension that represents its position in time, right? Then that would be a four-dimensional object, like it would be a four-dimensional space, and you could represent the movement of an object through time and space in one chart, right? And that would be like a map, a chart map, right? Of that object. Does that make sense?
Yes. Okay, I see. So you're saying you want to be so, whereas I see it's kind of as not caring about the specifics. You want to make sure that whatever chart map we're using is like definitely, well, in this case, a four-dimensional.
Yeah, I guess it was my point was like, I guess like maybe I have to let go of the idea of like you have to be able to create a specific chart map, like because like I always like when I was thinking to myself like, oh, is this a topological manifold? In like the examples he gave, I was like looking at specific, like he was looking at specific points and then seeing, can I make an isomorphism to a two-dimensional space or whatever, right? Or can I make a map that is invertible and continuous? And so in this like space-time is a four-dimensional space, that like intuition is now lost. Now you have to kind of like pretend that you are able to, but you can't really like grasp one in your mind just yet. You know what I mean?
I mean, do you believe that like at the tip of this pen or something, we could create a little map from here to a 4D matrix or something, or vector, you know, whatever, like a.
Yeah, I mean, I definitely believe it. Okay. I definitely believe it. Like, even like you could just think of like with the bottom number in the vector being like a time dimension, right? Then you could just like write the positions of the pen in space over the top three, right? And then you can imagine that if you just like slide along that fourth dimension, you'd see the pen moving through space. So I suppose that we can represent the movement of that pen in four dimensions quite well. And the question is does that mean that space-time is a four-dimensional manifold? Probably yes. Yeah, I think so.
So hang on, if I'm working in a chart here, like in my chart, my vision chart, whatever, I know it's not like specifically, but let's say I drop this pen and it seems to me that it's continuous. Does that mean that I can infer that? I mean, okay, this is basically like the last question of the lecture, but can I infer that the path of the pen in space-time is also continuous on the surface of it?
That's we'd actually have to go discuss like what a chart map is, and then then like is it ill-defined or not, you know what I mean? But to answer that question, but I mean, my question is for you, like, what is your vision map? You know what I mean? Like, can you tell me like what that means to you? Like
yeah, I guess that's the issue. I don't think of it specifically. I'm just like that, whatever, vision map. But if I was to have to answer that specifically, I don't have a good answer because of the fact that time only appears to move forward in one direction. But I guess exactly. My brain, I can make the pen be like, oh, look, the pen is going upwards, it's going backward in time. So maybe that's a chart. With your eyes, it's like not a chart, but then in your brain, maybe it's a chart.
Your brain, yeah. I don't really like, I can rewind the movement of an object in my brain, but I don't know if I would consider that a chart. Yeah, this is like a really interesting question, but yeah, we could like probably talk about it for like a long time. Anyway, so like that idea of like space. I mean, okay, well, an easier example of the value of a topology might be that like the movements of something on a desk, right? Like it's three-dimensional space, right? But we can now put that on a two-dimensional manifold. We consider the desk to be a two-dimensional manifold, and then we could do some interesting stuff with the two-dimensional manifold. So that might be like a value of it, right? Does that make sense?
Yes. Okay, but yeah, dive into what a manifold actually is.
What is a manifold? Okay, so someone said this to me, and it blew my mind because I was just thinking of the formal definition, but I was talking to them about their topology course, and they said, yeah, I mean, I said, you know what? Well, actually, they didn't tell me they were like learning about topology, but we were talking about topology, you know, I said, do you know what a manifold actually is? And then they asked me, and I said, for each point in the topological space, there exists a mapping around the point such that and then he cut me off, or he started talking, and he said, yeah, that region is locally Euclidean. And I was like, oh, I didn't really think about it like that, because like he never said that in the lectures. That is really like what that means, right? Actually, sorry, what I said was, for every point in the space, there exists a region around the point such that, and then he said, the region is locally Euclidean. And I was like, oh, interesting. But like the formal definition doesn't really, I mean, it does encode that, right? But like I didn't think about that until he like said it directly. But yeah, so I mean, the formal definition, just before we go back to that, is that for each it's a topological space MO is locally Euclidean if for each point in the space P there exists a map X such that there exists a region around the point P, I don't know, we call it region R or something, such that there exists a map. So there's like a lot of nesting here, right? But really what we're trying to talk about is for like, pick a point, pick a region around the point, right? And then for that region around each point, there exists a mapping to a R dimension, for a three-dimensional manifold, there's mapping to a three-dimensional space. For a two-dimensional manifold, there's mapping to two-dimensional space. And the conditions on that map is that it maps to that space, a subset of RD or RN or whatever. And then it's invertible in both directions and it's continuous. And so yeah, that is the formal definition. I can write that down if you want. But I have access to this like board.
Do you have like an iPad or something to write stuff or not?
I don't, but I can scribble it on my phone or something if you send. How do I do that? By the way, how do I is this like on your phone or your thing?
The way that I'm writing?
Yeah.
I've got like a full-on board that I'm using.
Oh, okay. Okay. But no, I'm saying like, is that something that is collaborative, or is that just like one way?
Oh, it's collaborative. Yeah.
Can you send me the ways to collaborate?
Well, I mean, if you join on your phone, and probably like, the link I sent you or something.
Oh, okay, interesting. Oh, so in Zoom, it's natively collaborative.
Yes, this is like native Zoom type of stuff.
Fascinating.
So let me see. I just accepted your phone. Let's see. Maybe don't accept the audio though.
Yeah, I got it.
Recording in progress.
Okay, that is not what I wanted. Okay, cool.
You're muted, bro. I muted both so that the looping would stop.
No problem. But how do I draw on this now?
There's going to be a button somewhere on your phone to annotate, like along with the chat, participant, security, video, whiteboard, remote control. There's gonna be one.
Yeah, I got it.
Cool. All right. So yes, you were explaining. Oh, I was asking, is there a restriction on the neighborhood? How do you choose the neighborhood? Because like if we're talking about R2, what if I chose this neighborhood with the edges actually selected? How could you map this into RD?
With the edges actually selected, how could you map that into RD? Oh, right. Yeah. So the point is there exists a region in the topology, right?
Okay. So it must be.
Yeah.
Okay.
Yeah. And so like you are using both parts of the topological space when you're constructing that. Because if it was just the point at any region, then the choice of topology wouldn't matter, right? You know what I mean? And so that's why the region must be in the topology.
Okay.
Yeah.
Yeah. So do you want to spell out the full definition for me of what a manifold is? If you want, do that.
Yeah. It is okay, this is not gonna work. Okay, let me try like it's just like gonna be big enough to do that. I mean, I don't have to do it. I mean, did you were you satisfied with the definition, or was that like that one source of ambiguity like kind of led you to believe that maybe I didn't like have a full grasp on it or something?
No, I don't know. It was just, for me, the way I like to think of manifolds is that we have the three conditions for a topological space. And then for me, manifold just means add a fourth condition, which is the one
Uh,
Google, Euclidean, whatever.
Yeah, that makes sense. Yeah, it's a very long fourth condition, but like it's definitely that is like a makes sense. Yeah, you have to meet the first three and then you have a fourth. That's kind of a cool way of thinking of it.
Yeah. So maybe do this. Explain to me a few examples of manifolds and how you build up to it being a manifold.
Okay, yeah. So a couple examples of a manifold, right?
But do it like constructively, right? Like, how do I trust that it is a topological space, whatever?
Yeah.
Okay.
Yeah, I got it. Like there's like um it was interesting because so with these invariants, right? What is the proof of like a certain space being in like Hausdorff or something, right? Like I was thinking like, oh my God, this like proof this Hausdorff proof is kind of annoying, right? Like I'd have to do all this stuff. But like because it's an invariant, right? I think the common way to prove a space is Hausdorff is that you just find an isomorphism to a space that you know is Hausdorff, right? And it's an invariant, and so in this situation, like maybe you could like argue. Anyway, so like I'm just saying, like constructive makes sense to me as like another way you have to prove. By the way, how do I write on like my computer now?
I mean, you can just use same thing. You have to find the annotate button and then just
Yeah, where is that button?
it's gonna be beside the participants chat, whatever, one of those.
Oh, I don't have that. The button doesn't exist. No. What the heck? Okay.
There's
Oh.
no annotate, no.
There is, oh, here it is, view options, and it's at the top for me here. Okay. But
Okay.
so here is like an example of, so imagine we have like a two-dimensional space, right? Or like even R3, it doesn't really matter. But like this like squiggly line here, this would be
Wait, before you even get the squiggly line,
Yeah.
what is this?
Yes, this would be R2, right? And then it's not enough to just say it's R2 because we have to like equip it with a specific topology. And
What is R2? How do you get to R2?
Okay, so R2 is it's just like, you know, are we like, how do I get to R2? Well, we've constructed the reals before, right? Do I have to go to that level? Or, so let's say we have the reals, right? And then, you know, we have like the Cartesian product that like, you know, creates these ordered tuples, right? And so R2 is like is equal to like the Cartesian product of two R's, which means that it's kind of wait, hold on, how do I get back to my pen? Okay, and so we have like draw, okay, we have like R cross R, right? And that becomes like 0 0 comma 0, and then it's like 0 comma 1 and like all this stuff, right? And so R2 is like a huge set of ordered tuples, right? Does that make sense?
Yep.
And then so I mean, kind of, if you think about it, R2 doesn't really have any structure, so like this, me adding these arrows is kind of a nonsensical thing if all we have is like a list of ordered tuples. And so if you equip it with the standard topology, what we're saying is, well, we're not really, this is like another thing where the analogy is quite tenuous, but we're saying like all closed sets are close to each other, right? That's kind of what we're saying. And so like, then it kind of makes sense that in like this random boundary, like let's call this a closed set here, then like all the points are kind of close together. And in this closed boundary, all the points are close together, right? And so we can kind of think of it a bit more like a plane, right? Like R2 kind of, we're adding some structure to it, so it's kind of like a plane.
Do we have enough structure to put these arrow lines or no?
Do we have enough structure with arrow lines? I believe so. Well, like what the arrow means is that we're
I could just stretch the plane in some really freaking weird ways, and then like I don't think we've talked about coordinates yet, so I don't know if that's proper.
Fascinating. Well, I mean, what I'm doing is like when I draw this is like we're talking about a visualization of an ordered set. of a set of ordered pairs equipped with some topology, right? And so I can just tell you like, okay, the set, in this direction, like, and we're just visualizing. So doesn't have to be like rigorous mathematics, right? But we're saying that like when we go in this direction, this corresponds to the ordered pairs, right? Like this number here, this is getting larger. The second number is getting larger when we go up here, right? And in this direction, the first number is getting larger. And so what we're just kind of like for each point on the thing, and we can also just add these tick marks. So I don't know if like I think you might have to like have a metric space or something like that to do this rigorously. But I'm just saying, let's like consider this like large like set of ordered pairs. Just throw each point onto the map, right? Onto this visualization.
Okay.
And these arrows mean that these numbers are increasing in such a manner, right?
Okay.
And then rigorous. So then what does this like squiggly line even mean? It means that consider the set, right? The set of like all the numbers that correspond to like the ordered pairs of like all these points. So like if this was 1 1, then 1 1 would be in the set. If this was 2 1, then 2 1 would be in the set, right? Or whatever. You know what I mean? And so consider all of that as a set.
How do you enforce that 1 point is and 1 point isn't? I mean, I assume it's some form of comprehension or like restricted comprehension or something.
Yeah. So it could be like it's like, we have a set S equals we have all like R1. Okay, well, we know like R1, like, yeah, so we're doing restricted comprehension over R2, right?
Okay.
And then what is like the conditions on R1? It could be like something as simple as like, for the circle, we have like some x squared plus y squared equals.
If you wanted to restrict to the circle, but okay.
Yeah.
Cool.
And so like there's like there might be some like relation of these two variables that generate this thing, and then we could say like, hey, if the set meets, if these like two variables meet some conditions, then it's in the set. And so it's just basically a form of restricted comprehension. But I don't know how you'd make such like a wacky line in in actual like what the actual restriction might be. But okay. And so now, so let's say we created the set, right? And so this is just like one way of representing that set.
We've created the can we call this the curve?
Yeah, we'll call it the set. We'll call it S. So
Okay.
that this curve, we've created S, right? And
then you haven't, wait, is R2 a topology yet? Have you decided to equip it with a topology?
Right, yeah. So the space we're considering here is like R2 equipped with the standard topology on R2.
Okay.
And so now I was like, we're trying to give you an example of topology. S itself is not a topology because it doesn't have we gave, this is a set. We need to make this a topological space. We need to equip it with a topology itself, right? And so what is the topology we're going to equip it with? We'll take this space as, well, like first is the set, right? And then this topological space we're going to equip it with is the subset topology on R2.
Why not choose like the chaotic or something?
Yeah, so that would not lend it. Well, we can do it constructively as we get into the things. I'll show you the counterexamples of why it wouldn't work with like the chaotic topology. Now, what is the symbol for the subset topology? I actually don't know. Do you know?
I don't know. Just go O sub or something.
O sub.
I guess.
Yeah, that's good. Okay, O sub. Very nice. And so like let's just like make sure we have an intuition on what that is, because like I'm not going to do the formal proofs, but we can like argue based on what we like understand this subset topology to be. So basically like we have a bunch of like open sets in like the standard topology. Like they all look like this, right? Like, you know what I mean? And they're of varying sizes, so they could be like really big too, right? Like we understand that these are the elements of the standard topology. Does that make sense?
Yeah.
And so we take, for each element in the standard topology, we take the intersections of the standard topology elements with the element that is in we take the intersection with like the set, the total set. And so like in this example here, like we have this bigger set, right? And what do we end up with? Oh no, I can't even undo that. That's super sad. We like lost the star of the show. But So in this like example, like we have this like subset, we have this like object here, right? Oh, sorry, we have this open set that's an element of the standard topology, and we're intersecting it with the line. And so we end up with this this open set here that kind of looks like this. The intersection would look like this. So it's like open on both sides, right? And then it's like an interval between it, right? And so we get like a bunch of open intervals of varying sizes. And we also get the entire thing too. Like we get the whole thing as well, because there's like a huge thing around it that when you intersect it, it's included as well. That's what O sub is. And so now when we argue like about like when we're trying to pick like, okay, so now let's just check all the things of like, is it a topological space, right? So
well, no. The point is the fact that we were O sub is purposefully selected in a way where it's already pre-proved that it'll be a topological space. What I'm curious about is if it's a manifold. Okay,
so you could, yeah. So constructively, right, there's like 4 conditions of like us checking if it's like a topological space, and then there's like one more for if it's manifold, right? And so I guess we kind of know, like, because of how we construct subset topologies, that the first 3 are kind of like, or we get them for free, right? And so we can kind of conclude already just because of like how we construct the subset. Topological space is indeed a topological space like S and O sub, right? Now the question is this specific topological space a manifold? And so what is, now I have to kind of write it out. So it says for all points that are the element of S, right? There exists a let's call it a region. I don't know what the actual thing. Region, which is an element of, what is it called?
Usually U. The letter U for neighborhood.
That makes sense. Yeah, neighborhood. Okay, that's good. I need to remember that because I always forget. There exists a U element of the O sub, right? Such that that there exists a map X that maps from, well, for like, this is for n dimension, right? N dimensional manifold, right? And so we first said, we haven't even discussed like, is this a 1-dimensional, 2-dimensional, what manifold is? I'm gonna make the claim that it's a 1-dimensional manifold, right? And so that maps a U. So this map X, we're talking about U, maps U to fuck, right? Oh man, I can't swear, it won't make it onto the YouTube channel. Okay, there exists a U that maps X, which is a map that maps U to, because we're talking about 1 dimension, and it's R1, right? So just R1 is such that, like, and then X has to meet these like 3 conditions, like 1, 2, and then 3.
By the way, I think I'm just going to add this somewhere, but I believe P has to be a part of U. So the neighborhood you choose has to contain the point.
Oh, right. Yeah, that is totally true. Yeah, I forgot that. And then X is invertible from R U to R, right? R1. And then it's like, I guess this is like, someone showed me this vice versa symbol. So it's like true the other way around too. So X is invertible from R1 to U. And the third is that X is continuous, right? Continuous. And the question, one question I had from this definition is that is like, or this is just something that I, crossed my mind when I saw this, was like, if it has to be invertible both ways and continuous, does that imply it's continuous? And by the way, like, I believe this continuous here is from U to R. So it's not saying something about continuity both ways. It says this is actually just a statement about continuity in the forward direction. And then my question was, does this imply that it's like continuous in the opposite direction? And I think it's a pretty trivial proof that it is. So it's continuous in both directions. Actually, is like, one way you can think about it. But yeah.
How do you go about showing that proof? Like, just sketch it.
So So basically, continuous from U to R means that the pre-image of the points that land from the map into R exist in U. I think I'm just. I remember thinking through this in my head when I did it, and it was actually pretty simple. But I'd probably have to go look at the definition of continuous, which is escaping me right now. It's something to do with the pre-image of.
Open sets are open.
Yeah, well, the pre-images of open sets are open, right? And so, and we also know that that is true from U to R. Now we just want to show that's true from R to U, and I believe it's like literally something as simple as because it's invertible in that direction, then we know that if and invertible means that I think you also have to look at the topology somehow, right? Because like open sets are open means that it's an element of one topology another. I think this is two lines. It's just kind of escaping me what the implication is.
But I mean, I think it's not true, by the way.
Oh, you don't think it's true?
Not at all. Because there's a funny extreme example, a funny monster, where if you equip literally any set with the discrete topology, it'll instantly be a manifold. Reason being that pre-image. So the question is the existence of this map X, and the map is always going to be continuous if the pre-image of open sets. Oh, I'm sorry, not discrete. If this is the chaotic, right? Because there's only two examples to check. So yeah, so this will always be a manifold. In practice, what happens is to avoid monsters like this, the definition of a manifold requires the topological or the topology to be Hausdorff, which is just to make sure that it's not chaotic, essentially.
Okay, so, interesting. So it's just continuity in one direction. That's interesting to me.
But the way that you could have proved that it was continuity in both directions is if you require the definition of a manifold to be Hausdorff for the topology to be Hausdorff, then naturally there'll be a certain amount of structure on the U, and then you can show that that means that.
Okay, that is super interesting. Yeah, remember he when he was discussing Hausdorff, he was or like compactness, then he was like compact spaces are like what you wish your topology was because you can do certain proofs. That is like an example of a situation where there's like probably some outliers or some.
Yes.
Okay, cool. That's like a really cool thing. But like in I guess in the typical case, the median case, this is true, but not in every case. So,
but no, if you require the topology to be Hausdorff,
right.
then it will always be true. Yeah. Okay. Cool.
Yeah. But the other thing to me is like maybe I don't really understand. I mean that I can tell you the definition of continuity, but I don't really intuitively grasp it just yet. Remember we did this last week. It'd be really cool for me to, if that video existed, to go watch what we did again, because I kind of slipped my mind as I was considering some things with respect to continuity this week. But I'll probably have to go review.
I mean, if you
we talked about last week.
Fair point. If you want, I don't know if you remember the example with the This one is like my go-to because it's so beautiful.
Yeah, I'll just review that after. Like I don't want to waste your time. But I remember that example. Okay, so we're getting back to like, is this a manifold or not, right? And so my claim was yes, it's a one-dimensional manifold, right? And so how can we see that? I'm not going to do the proof because the proof, well, I mean it is kind of similar, but basically like if you choose any point X, right? Like you choose a point here, then we have to find a neighborhood around X that is that can be mapped to R1, right? And so we know like what the neighborhoods generally look like. So if we just take the neighborhood that includes this point, right, this open neighborhood, like this is our kind of neighborhood U, right? Then we know it's in the topology because we just mentioned what the topology elements are, right? And then we can see that like it's just like this open interval, and so we could like map this to like get R1 here, right? And I'm going to add the arrows, and then we have to talk about like what the arrows look like. But we could just like map each point like this to here, this to here, right? And this to here. And so that would kind of be like a mapping for you, and so that would work for any point in the topology, including the end, because R1 goes on forever. So it doesn't really matter that we have like a closed set in the topology, because that would also be mapped to R.
No,
And that
no,
was-
those sets would definitely not be mapped to R, because the endpoint, the hard endpoint, has nowhere to go to.
Well, like no, I was using closed set in like a weird way, where I was like, imagine that. Remember how we have the element of the entire curve, including the endpoints in our topology here, right? And so, like, the question for me was, can we find a? Actually, it doesn't really matter anyways. This is another thing I was thinking about, like, because we don't actually care about everything in the topology, right? Because all we care about is for each point there exists a topology such that there exists a neighborhood such that it can be mapped to Rn, right? And so we would never really care about the entire curve, right? Because we only care about specific points on the curve. And then for those points, we can choose like a smaller neighborhood. We don't have to choose the whole neighborhood. But
I mean, if the curve here is filled in at the edge, I believe it fails to be.
yeah, I do agree with that.
Okay.
Because there is no open neighborhood, including just the endpoint,
Yes.
right? And so like that fails because there's no neighborhood, right? So you can't find the U. But
So I
but if
don't, the curve you drew, does it go on for infinity in both
no,
directions?
I actually I actually so this is interesting. My intuition, my like I intuitively meant it was like an open curve. So there's like,
Oh, okay, that the ends are okay.
and but if it goes on to infinity, I believe it also you're able to do the same thing, because it doesn't really matter. Like you could just shoot for any point, even though there's an infinite amount of points, you can still just find a neighborhood.
Yes.
Now, if the topology definition said something about all the neighborhoods, that's like interesting to me, because like Rn would be a neighborhood, right? And then that's like it's it's countably infinite. And question, and then I don't actually know if we're able to map a count. Like now it's obvious to me that we can, right? Because Rn, you know what I mean? Like we can, but that wasn't immediately obvious. I was just thinking to myself, like in my head, we don't even have to worry about that, because all we care about are specific points. Yeah.
Question here. If you did have this going off to the endpoints, couldn't you just select the neighborhood to be M, to be the whole, or in this case, S, I think was the letter, and then the map to be mapped down to here?
Yeah, and that's what I was saying. So I believe it is possible. Yeah, I definitely think it's possible, because like R1 in the situation is a countably infinite space, right? And
Okay.
if this line goes on to both directions, it'll M or S will be a countably infinite set as well. Actually, is it countably infinite or uncountably? It is uncountably infinite, right? If we're talking about R, right? Rn
Yeah.
or R1. But both are uncountably infinite. So they're cardinality matches. So there does exist some bijection between the two. And that is kind of what we're looking for. So yeah.
Okay, there's two directions you can go to continue your explanation here. First of all, you could give more examples of manifolds, like a sphere, a donut, or a branch.
Yeah.
Or you can talk about what a chart is, an atlas is, what a chart map is, coordinate maps.
Yeah. So I think we should go the second direction, because I kind of like understood those definitions quite well. Like the examples, like they made sense to me.
Maybe for a fun one, show that a branch is not a manifold.
Yeah, so like let's just like use this exact same thing. Actually, let me just, so we kind of, I mean, this is recorded, so I can just erase this stuff.
Okay, do you want me to be clear, by the way?
What, sorry?
Clear the board?
No, let's leave the definition up
Okay.
for fun. Okay. And so I guess my point was, so we have a two-dimensional space, right? And then we have a two-dimensional space, and then we take this point, this curve, right? And it's open on all these points, right? So is this a one-dimensional manifold, or is this a two-dimensional manifold? Maybe it is a two-dimensional manifold or something. But the point is, for this point in the middle, right? Well, it's definitely not a one-dimensional manifold because at this point you can't choose, and this thing here with the standard topology, right? There's like a open set that includes this, and then it also includes this, right? But there's no open set that just includes one part of the branch. Like if you have any open set around the branch but include both ends of the branch, like all three ways that it kind of goes out. And so in those three branches, right, there is no map in the three branches that is invertible to R1, because I mean, intuitively, you think about it, you step in one direction of the branch, you step in the other. How could that be invertible? Because that information of which branch you stepped on is lost when you go to R1, right? And so it's not invertible. You're losing information. So
Okay. Makes
kind
sense.
of, it's not it's not locally Euclidean in some sense. So it fails on this condition here. X's are invertible from actually, it fails on the first. So
And it probably would also fail for the second one.
yeah, I think so. Yeah, I actually wasn't
Oh,
sure
sorry, the
which
third
one.
one. The third one I meant continuous. For pure image of open sets is open.
Yeah, I wonder how that map would actually look. Like it'd be a pretty funny map. Like
Yeah.
you'd have like overlap between these two
Oh
things.
no, well no, X is invertible would definitely happen. Because there's a way to map this into R2, no problem at all, or whatever.
No. XR1, you can map that, right? But you can't go backwards without losing information, I believe.
Yeah. Well, if you're talking with just sets, they're both uncountably infinite, so the bijection will exist. The issue is with continuity.
Right. That actually is a good point, because like you can imagine like just some funny example is like you map like for this like branch here you map to even numbers, and this branch here you map to odd numbers, right?
Sure, yeah.
Or whatever. But the problem is that it wouldn't.
Continuity gets fucked though.
Yeah, the continuity wouldn't work. But there is a way to preserve the information. The thing is, like, for countably or for finite sets, you can't go in that direction without losing information, right? But like with the funny thing is that because it's infinite, you can kind of like find space in between, or you can pack the information in,
So
which is kind of interesting. Like you can put two countably infinite sets in another countably infinite set, which is like kind of interesting because like the information shouldn't be able to fit, but it does anyways, which is kind of interesting. Okay, so that was like branches. Let's talk about like chart maps and atlases and stuff.
Yes. Do you want me to clear?
Yeah, let's clear.
Cool.
Okay. So remember how we had that X map, the map X that takes like some, I'll just draw it again. So we have like this like curve, right? We have this interval on the curve, right? This neighborhood. We call the neighborhood U, right? We call the map X, right? X is the map, right? And so we just put back brackets around them, and that's a chart map.
Mm-hmm.
You satisfied with that definition or not?
I don't know if it's a chart map, but it does look to me like a chart.
Oh, that is a chart, right? And then actually so this itself is called the chart map, like the X inside, yeah. So that is, but U and X together, because you need to know like what domain the chart map is defined on. So that's why it's called a chart when you put it together. This is CM, and then the whole thing is C.
What about an atlas?
Right, and so like an atlas is a collection of charts, and so it's kind of interesting because like, yeah, basically like you have it, from colloquial words, right, from like English. Like let's say you had a chart that charts the Atlantic Ocean, you have a chart that charts the Pacific Ocean, right? So you put them all together in a bundle called an atlas, right? Because the atlas is supposed to chart everything. And so what is the condition on? Okay, so chart map, an atlas is kind of like a collection of U1, X1, right? And then more of these, right? So there's like a bunch of different charts in it, right? And the condition is that such that the union of U n for all n, like, n elements are, whatever, all the n's. This is my shitty notation for all the u's equals it equals the what do we call it before? The set. We call the set M.
Yeah, let's just say M, the manifold. Yeah.
The manifold. And so basically the idea is you can recover the entire manifold by looking at each parts, like layering them onto each other or whatever. And that makes an atlas. Does that make sense as definition?
Yes. So when you say it's this set of charts, does it have to be every single freaking possible chart, or literally just the minimum possible such that this condition is verified?
Yeah. So the definition is that it's the smallest possible atlas is the minimum, but it was interesting. I don't know if I had a lecture and I saw this, but he said that like removing atlases is kind of like removing things from an atlas is like an information. You're adding information, right? You know what I mean? Because if you have and so you're removing things, you're kind of adding information, and so I don't know. I remember the
reason for that is kind of sneaky, and it has to do with like smoothness, but
interesting. But I mean, it kind of makes sense if you like argue from information theory, right? Because if I give you like an atlas, right? Like I could tell you how to construct it in n steps, right? Like that is and that might be like the cheapest possible encoding for the entire atlas, right? Like tell you how to build it, and then like to build it, and then like build it without some elements, right? Like if you assume that there's an encoding that is smaller than the whole thing, right? Then like build it minus this and this and this is like adding information, right? But then you'd have to like know the encoding, and so it's not like exactly like a home run analogy, but like the point is if you assume there's like some easy way to build the atlas, then like that thing makes sense. But all that to say that like it just a reinforcement of situations where you can have different atlases of different size for a specific M, right? Like they can be bigger, they can be smaller, they can be like a lot of overlap or very little or whatever. Yeah.
So then what's a coordinate or the coordinate maps?
Yeah, so this was one thing I was kind of quite interested in. I didn't really understand this. Can you give me 1 second to get some water real quick? Because I need to. That show?
Yeah, sure, yeah.
Cool. Coordinate maps. What was interesting to me about that was okay, so let's just like introspect on this like map X, right? Like let me erase, but like, and I'm actually might fumble this a bit because I'm not sure if I exactly remember, but like so let's say like
for context, coordinate maps are one of the things that at first I felt were so unimportant, but then for some reason they get used like freaking everywhere, which was a bit weird.
Interesting. But okay, so like let's say this like M comma O, right, is 3 comma D manifold, right? And then let's say we like have this, like let's say, and then let's say X, U comma X is a chart. I think is a chart. I think you have to say of the topological space, right? Like of MO, right? Like you can't just say it's a chart. You have to like say it's a chart of MO, right? Does that make sense or no?
I'm trying to see why.
Well, I mean, you can't just say it's a chart. Like, what is it a chart of? Right?
Yeah, I guess you have. Yeah, well, for the condition to be a chart, X has to be like whatever invertible continuous, and to check those conditions, you need the M and the O. So
yeah,
that's it for one.
That's a good one. Okay, so and then also it's kind of implicit that X is a map from M to R3, from U to R3 here because I said three-dimensional. But you know what is interesting is that in this definition, I said, hey, this is a three-dimensional manifold, but I didn't tell you like what higher dimension is being mapped into R3, right? So like M right now, I didn't tell you, like maybe M is like a subset of R6, maybe it's a subset of R9
Sure.
or whatever. And so I don't know how we specify that information. Maybe we could just like M subset of R9 or something. Maybe that is like the right way to do it. I don't know. Do you have like an opinion on this, by the way?
I think that doesn't matter at all. Whether I construct a circle in R2 or in R3, you know.
Oh, well, I mean, I think it definitely does matter because if you look at X, right? X maps from U to R3. We know the domain, right? But then if you look at but then like, you know, U might be like a subset of, this is my opinion, this is why I was confused. U might be a subset of R9 or R6, right?
Sure.
And so like, wouldn't the internals of the map look quite different in these situations, or what do you think?
So
Or would they
imagine
not?
you're in R2 and you sculpt away at R2 and you're left with the circle with x squared plus y squared equals 1. Now imagine you're in R3 and you do the same exact thing. You sculpt away at R3 using x squared plus y squared equals 1. Yes, the U over here is going to have coordinates x, y, and this one's going to have x, y, 0 to whatever for the local chart. But that doesn't matter. I don't know.
It doesn't matter. That is really interesting. I think that is fundamentally the thing that I was misunderstanding, right? Because like if you have a donut, right? If you have a donut, for me, like that felt like it was a very three-dimensional thing, right? You know what I mean? Felt like it was three-dimensional. And
Well,
so
the circle, does the circle feel two-dimensional or three-dimensional?
well, it feels like a very two-dimensional thing. But you
Okay.
could apparently, but I agree that you can embed it in three dimensions. You could shave away from three dimensions to get a two-dimensional thing, and so the information is the same. In either case, right? The information that's being encoded in the set is the same in either case, right? Although like this, you know, I think we agree that these two sets are not the same, right? Because there's like a zero element here, right, in each of these.
I disagree. I mean, the whole point of classification of sets is that two sets behave the exact same way if they have the same cardinality.
And these sets do have the same cardinality. But you know, that point of yours, yeah, okay. I guess the point is any circle anywhere behaves the same way. A circle stretched in any ways behaves the same way.
So, I mean, I guess I said their cardinality, but in this case, we're actually talking about topological spaces. So I should have said that as topological spaces, these two circles behave the same because their subset topologies are going to be the exact same copies of each other.
Yeah, that makes sense. Okay. But anyway, so then I guess my point is, okay, well, let's get back to coordinate maps, and then like I guess that like confusion of mine will like start to show like why it was even relevant. The point is, this map X, if we introspect, like it's map X is mapping like some things here, it's mapping some things here, right, to a three-dimensional vector, right? And so there's like x1, x2, or actually, I'll call it
Here,
R.
I think I know how to resolve your confusion.
Yeah.
You know the U?
Yeah.
The U is an element of the topology, not of the M. It must be a neighborhood, which is defined to be an open set. Therefore, for the circle in R2 and R3, even though this one may have an extra coordinate, in terms of open sets, they'll be defined the same.
Hold that for a second. But these open sets, they won't have an extra coordinate, or no? They will still.
Huh, I guess they will. Weird.
Yeah, I didn't quite understand that. Just because like the map X has to be like well defined, right? And like I didn't understand why like we're just dropping this coordinate. And so like in his lecture he like said, well, let's assume we this X is specified on this domain U, and there's there's n elements, because n dimensional manifold, n elements, right? It's getting mapped to like n elements in R1, right? And so this specific map of X1 to R1 is called a coordinate map. It maps one coordinate in the manifold to one coordinate the uh in the what is it called? What is this other thing called? It's in the chart, right?
Yes.
Chart. So this like specific map here, which is like it's n-dimensional map, right? It was just like a one-dimensional map. It maps from X1, which is a subset of R, to
Oh,
R1,
no. I think, wait a sec. You're establishing coordinates on the manifold. I don't think that's allowed. Rather, all three of these contribute to this guy. All three of these contribute to this guy, and all three of these.
Okay. That does make sense. Yeah. Yeah. So all three being, yeah. So it's a map from
U to R. Yes.
from U to R. Yeah. Okay. For sure. That makes. I don't know. I for some reason like that made sense. It makes a lot of sense. I remember reading the definition. I thought it was the other way around. So I got to read the definition again. And now I don't really know why this is even relevant. It seemed pretty unimportant to me as well. But I mean, it's kind of like, it kind of, in some sense, it does like seem important, because it's like, yeah, I don't know. I can't really speak. Do you have any questions about these?
No.
Okay, but they'll probably show up later or something.
Yeah. For some reason, they show up a shit ton, which is really weird.
Interesting. Very interesting.
I mean, I can try to explain. It's so random. Like to me, I sort of didn't get why, but because it's a map from U to R,
yeah,
it means that for every point in the neighborhood, you're assigning, think of it as R, if you're assigning a temperature in a sense. And then that temperature can be thought of as a function. And for some reason, that becomes really important. I don't know. It's weird.
Interesting.
But yeah, I don't know. Even though I guess it doesn't feel motivated to explain it, just the fact of having to explain it will make it easier to understand when the next thing comes up.
Makes sense. Okay, I have to go at 2. But
how about talk about manifold philosophy real quick? Like, why do we care about charts, and does the behavior of charts translate into the behavior of the total manifold? So for continuity and then for differentiability.
Yeah, so we have like an n-dimensional manifold where something's happening, right? And so we have a chart where we chart it into our lower dimensional space, like of the big manifold. Well, the manifold is n-dimensional, right? But it could be embedded in a larger dimension, or something. Some whack shit could be going on with the manifold. But we could chart it down into like our really nice n-dimensional thing, right? Like the example that was given was, we have a globe, right? The globe is 3-dimensional, and we chart it into our 2-dimensional space, right? And then can we let's say the path is continuous on the globe in 3-dimensional space. Can we then in our chart, we have a 2-dimensional chart of that 3-dimensional space, can we make the conclusion that because this path is continuous in 2-dimensional space, it's also continuous in 3-dimensional space, right? And the answer that was given was yes. However, we have to be careful, because it might be ill-defined. Like the conclusion or the characteristic we're trying to conclude might be ill-defined, right? And so the danger is that if you're able to say something about continuity, right, then whatever chart you pick, it should be continuous, right? Like the path should be continuous, right? And so I believe that was shown, he said it was true. I don't think there was a proof for that.
Yeah, he showed true. Yeah. Using the chart transition map, he showed that if you go from chart to chart, you can also just go from chart to base manifolds back to charts. And
and that composition of map, composition of continuous map is continuous, and that's why it's continuous. And it kind of makes sense to me because it kind of makes sense because you can imagine some random fucking distort chart, right? Like some weird chart that stretches things around, but it must be invertible in both directions, right? And so it can never really kind of break the continuity of the map because all we're doing is stretching, right? The continuity of the path. So if it's continuous one, we can stretch it all we want, and then it would.
What about differentiability?
Yeah, so differentiability is you can't do that, right?
Okay.
And the reason why is because
well, the chart transition map are not guaranteed to be differentiable.
Exactly, right? Because of the differentiability doesn't commute the same way, or it's not transitive.
If you restrict what charts you're allowed to use so that they are all differentiable.
Yeah, so that's like a different atlas, right? You know what I mean?
Nice. Okay,
But,
that atlas is called the smooth atlas. Okay, cool. And boom, now you've done smooth manifolds.
Yeah. However, this is what I was just gonna say is like intuitively, why is differentiability like not work depending on the chart you choose? Like how can you get a different like you have a differentiable path, right? Like you can imagine smooth path, right? And then you have like what is the not smooth chart that you can use?
Yes.
And I was like, maybe like you can kind of like take the smooth thing and wrap it around a corner or something, like really wrap it super tightly. Exactly. And then you get like a discontinuity. Well, it's continuous, but it's like a kink. It's like a kink, and kink is not differentiable. And so that was kind of like my intuition on why differentiability doesn't
it's the perfect intuition.
Doesn't work. But yeah, but then you could just like exclude those charts from your outline.
Exactly. Oh my God, bro, you've already done freaking smooth manifolds. Let's go. So by the way, for context, I think the next best lecture is the lecture 3 of the gravity and light one on tensors, multilinear maps, which is a little bit tensors. It's just cool for context. It's a really, really, really cool, neat lecture.
Oh, cool. I'll do that one next. I was doing 5, and I gotta say, it was a lot. Oh, one thing. Oh, dude, can I ask you this question about compactness while you're here?
Sure.
Okay. Yeah, wait, hold on. Can I pull up? So I was looking at intuition for compactness because I was kind of like having a bit of trouble wrapping my head around it.
Yep. Definition is that every open cover has a finite subcover or something, right?
Yeah. Okay. And let me can I find it? Okay. Here is my fundamental question, right? This is like something that is said about like okay, so like let's give the example 1, 2, 3, right? This set. Is this compact or is this not compact?
Depends on the topology.
But like, can you give me an example of a topology where it is compact?
Discrete topology.
Okay, so 1, 2, 3. Okay, well, every cover has a finite subcover. So like so in that example, right? Right? We have like comma O D or whatever, right? This is our space, right? And the thing we're trying to work through is every cover has a finite subcover. If I give you 1, 2, then I give you 3, right?
So it's a finite set. So naturally, all of the subcovers are going to be finite.
Well, hold on. We could. What is a subcover of 1, 2, 3?
1, 2, 3. It's just a subset that's finite. You only have to take the sub if you're forced to, because the original is not finite. But that's
okay. Yeah, that's what that was what was really missing. It was just that the thing didn't really make sense if it had to be sub.
Yeah,
right?
like A is the subset of A is true, right? So
yeah. Okay. Now I can go kind of tackle my thing.
Another really cool intuition that's really worth keeping in mind is T1, T2, compact. All of these invariants are just measures about the fineness and coarseness of a topology. Where the more fine it is, the closer it gets to the discrete topology, and the more these are going to be checkmarked. So just thought I would throw that out.
Interesting. That is interesting. Okay, cool.